The Foundations of Geometry by David Hilbert. Chapter 1. The 5 Groups of Axioms. Section 7. Consequences of the Axioms of Congruence. Suppose that the segment AB is congruent to the segment A'B'. Since according to the axiom 4,1, the segment AB is congruent to itself, it follows from axiom 4,2 that A'B' is congruent to AB. That is to say, if AB is congruent to A'B', then A'B' is congruent to AB. We say then that the two segments are congruent to one another. Let A, B, C, D through KL and A'B', C'D' through K'L' be two series of points on the straight lines A and A' respectively, so that all of the corresponding segments AB and A'B', AC and A'C', BC and B'C' through KL and K'L' are respectively congruent. Then the two series of points are said to be congruent to one another. A and A', B and B' through L and L' are called the corresponding points of the two series of points. From the linear axioms 4, 1 through 3, we can easily deduce the following theorems. Theorem 9. If the first of two congruent series of points, A, B, C, D through KL, and A'B', C'D' through K'L' is so arranged that B lies between A and C between B and D, then the points A'B', C'D' through K'L' of the second series are arranged in a similar way. That is to say, B' lies between A' and C', and C' lies between B' and D', etc. Let the angle HK be congruent to the angle H'K', since according to axiom 4,4, the angle HK is congruent to itself. It follows from axiom 4,5 that the angle H'K' is congruent to the angle HK. We say then that the angles HK and H'K' are congruent to one another. Definitions. Two angles having the same vertex and one side in common, while the sides not common form a straight line, are called supplementary angles. Two angles having a common vertex and whose sides form straight lines are called vertical angles. An angle which is congruent to its supplementary angle is called a right angle. Two triangles ABC and A'B', C' are said to be congruent to one another when all of the following congruences are fulfilled. AB is congruent to A'B', AC is congruent to A'C', BC is congruent to B'C', the angle A is congruent to the angle A', the angle B is congruent to the angle B', and the angle C is congruent to the angle C'. Theorem 10. First theorem of congruence for triangles. If for the two triangles ABC and A'B', C', the congruences AB is congruent to A'B', AC is congruent to A'C', and the angle A is congruent to the angle A', then the two triangles are congruent to each other. Proof. From axiom 4,6 it follows that the two congruences angle B congruent to angle B' and angle C congruent to angle C' are fulfilled. And it is therefore sufficient to show that the two sides BC and B'C' are congruent. We will assume the contrary to be true, namely that BC and B'C' are not congruent, and show that this leads to a contradiction. We take upon B'C' a point D', such that BC is congruent to B'D'. The two triangles ABC and A'B', have then two sides and the included angle of the one agreeing respectively to two sides and the included angle of the other. It follows from axiom 4,6 that the two angles BAC and B'A'D' are also congruent to each other. Consequently, by the aid of axiom 4,5, the two angles B prime A prime C prime and B prime A prime D prime must be congruent. This, however, is impossible since by axiom 4,4, an angle can be laid off in one and only one way on a given side of a given half ray of a plane. From this contradiction, the theorem follows. We can easily demonstrate the following theorem. Theorem 11, the second theorem of congruence for triangles. If in any two triangles one side and two adjacent angles are respectively congruent, the triangles are congruent. We are now in position to demonstrate the following important proposition. Theorem 12. If two angles ABC and A'B''C' are congruent to each other, their supplementary angles CBD and C'B'D' are also congruent. Proof: take the points A', C', D' upon the sides passing through B' in such a way that A', B' is congruent to AB, and C', B' is congruent to CB, and D', B' is congruent to DB. Then in the two triangles ABC and A'B''C', the sides AB and BC are respectively congruent to A'B' and C'B'. Moreover, since the angles included by these sides are congruent to each other by hypothesis, it follows from Theorem 10 that these triangles are congruent. That is to say, we have the congruences AC is congruent to A'C', and the angle BAC is congruent to the angle B'A'C'. On the other hand, since by axiom 4,3 the segments AD and A'D' are congruent to each other, it follows again from Theorem 10 that the triangles CAD and C'A'D' are congruent. And consequently, we have the congruences CD is congruent to C'D' and the angle ADC is congruent to the angle A'D''C'. From these congruences and the consideration of the triangle BCD and B'C', it follows by virtue of axiom 4,6 that the angles CBD and C'B''D' are congruent. As an immediate consequence of Theorem 12, we have a similar theorem concerning the congruence of vertical angles. Theorem 13, let the angle HK of the plane alpha be congruent to the angle H'K' of the plane alpha prime. And furthermore, let L be a half ray in the plane alpha emanating from the vertex of the angle HK and lying within this angle. Then there always exists in the plane alpha prime a half ray L prime emanating from the vertex of the angle H'K' and lying within this angle, so that we have the angle HL is congruent to the angle H'L', and the angle K, is congruent to the angle K'L'. Proof: we will represent the vertices of the angles HK and H'K' by O and O' respectively. So select the sides H, K, H', K', the points AB, A', B', that the following congruences are fulfilled. OA is congruent to O', A', and OB is congruent to O', B'. Because of the congruences of the triangles OAB and O', A', B', we have at once AB is congruent to A', B', the angle OAB is congruent to the angle O', A', B', and the angle OBA is congruent to the angle O', B', A'. Let the straight line AB intersect L at C. Take the point C' upon the segment A', B', so that A'C' is congruent to AC. Then O'C' is the required half ray. In fact, it follows directly from these congruences by the aid of axiom 4,3 that BC is congruent to B'C'. Furthermore, the triangles OAC and O'A'C' are congruent to each other, and the same is true also of the triangles OCB and O'B'C'. With this, our proposition is demonstrated. In a similar manner, we may obtain the following proposition. Theorem 14. Let H, K, and L and H', K', L' be two sets of three half-rays where those of each set emanate from the same point and lie in the same plane. Then if the congruences, the angle HL is congruent to the angle H'L', and the angle KL is congruent to the angle K'L', the following congruence is also valid, namely, the angle H, K is congruent to the angle H'K'. By the aid of the theorems 12 and 13, it is possible to deduce the following simple theorem, which Euclid held, although it seems to me wrongly to be an axiom. Theorem 15. All right angles are congruent to one another. Proof. Let the angle BAD be congruent to the supplementary angle CAD, and likewise let the angle B'A'D' be congruent to its supplementary angle C'A'D'. Hence the angles BAD, CAD, B'A'D', and C'A'D' are all right angles. We will assume that the contrary of our proposition is true, namely that the right angle B'A'D' is not congruent to the right angle BAD, and will show that this assumption leads to a contradiction. We lay off the angles B'A'D' upon the half-ray AB in such a manner that the side AD' arising from this operation falls either within the angle BAD or within the angle CAD. Suppose, for example, the first of these possibilities is true. Because of the congruences of the angles B'A'D' and BAD', it follows from Theorem 12 that angle C'A'D' is congruent to the angle CAD'. And as the angles B'A'D' and C'A'D' are congruent to each other, then by axiom 4, 5, the angle BAD' must be congruent to CAD'. Furthermore, since the angle BAD is congruent to the angle CAD, it is possible, by Theorem 13, to find within the angle CAD a half-ray AD' emanating from A, so that the angle BAD' will be congruent to the angle CAD', and also the angle DAD' will be congruent to the angle DAD'. The angle BAD' was shown to be congruent to the angle CAD', and hence by axiom 4, 5, the angle CAD' is congruent to the angle CAD'. This, however, is not possible, for according to axiom 4, 4, an angle can be laid off in the plane upon a given side of a given half-ray in only one way. With this, our proposition is demonstrated. We can now introduce, in accordance with common usage, the terms acute angle and obtuse angle. The theorem relating to the congruence of the base angles A and B of an equilateral triangle ABC follows immediately by the application of axiom 4, 6 to the triangles ABC and BAC. By the aid of this theorem, in addition to Theorem 14, we can easily demonstrate the following proposition. Theorem 16. Third theorem of congruence for triangles. If two triangles have the three sides of one congruent respectively to the corresponding three sides of the other, the triangles are congruent. Any finite number of points is called a figure. If all of the points lie in a plane, the figure is called a plane figure. Two figures are said to be congruent if their points can be arranged in a one-to-one correspondence so that the correspondence between segments and the corresponding angles of the two figures are in every case congruent to each other. Congruent figures have, as may be seen from the theorems 9 and 12, the following properties. 3 points of a figure lying in a straight line are likewise in a straight line in every figure congruent to it. In congruent figures, the arrangement of the points in corresponding planes with respect to corresponding lines is always the same. The same is true of the sequence of corresponding points situated on corresponding lines. The most general theorems relating to congruences in a plane and in space may be expressed as follows. Theorem 17. If A, B, C, etc., and A', B', C', etc. are congruent plane figures, and P is a point in a plane of the first, then it is always possible to find a point P in the plane of the second figure, so that A, B, C through P and A', B', C' through B' shall likewise be congruent figures. If the two figures have at least 3 points not lying in a straight line, then the selection of P' can be made in only one way. Theorem 18. If A, B, C, etc., and A', B', C', etc. are congruent figures, and P represents an arbitrary point, then there can always be found a point P' so that the two figures A, B, C through P and A', B', C' through P' shall likewise be congruent. If the figure A, B, C through P contains at least 4 points not lying in the same plane, then the determination of P' can be made in but one way. This theorem contains an important result, namely that all of the facts concerning space which have reference to congruence, that is to say to displacement in space, are, by the addition of the axioms of groups 1 and 2, exclusively the consequence of the 6 linear and plane axioms mentioned above. Hence, it is not necessary to assume the axiom of parallels in order to establish these facts. If we take, in addition to the axioms of congruence, the axiom of parallels, we can then easily establish the following propositions. Theorem 19. If 2 parallel lines are cut by a third straight line, the alternate interior angles and also the exterior interior angles are congruent. Conversely, if the alternate interior or exterior interior angles are congruent, the given lines are parallel. Theorem 20. The sum of the angles of a triangle is 2 right angles. Definitions. If M is an arbitrary point in the plane alpha, the totality of all points A for which the segments MA are congruent to one another is called a circle. M is called the center of the circle. From this definition can be easily deduced, with the help of the axioms of group 3 and 4, the known properties of the circle. In particular, the possibility of constructing a circle through any 3 points not lying in a straight line, as also the congruence of all angles inscribed in the same segment of the circle, and the theorem relating to the angles of an inscribed quadrilateral. The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice. This ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Wrenholt. Programming and illustrations by Jim Wrenholt. 2019. Portrait of David Hilbert by Reida Wrenholt. Thank you for listening.